Okay, hello everyone, and welcome to Science at Home. Just a reminder, my name is Anna, and I am here today with the one and only director of Armagh Observatory and Planetarium, Professor Michael Burton. Hi, Michael.
Hi there, Anna. How are you?
So we've got a few questions for Michael today about his area of expertise. So the first question I have for you, Michael, is how large is the Milky Way?
How large is the Milky Way? Well, a Milky Way, first of all, is our galaxy. It's our star city. It's our home in the universe. How big is it? Well, if you look into a textbook, it'll probably say 100,000 to 200,000 light years across. That means it takes light that length of time, that vast amount of time to get across, traveling at 300,000 kilometers a second.
Wow.
But actually, the size is not that well defined. It doesn't really have any kind of edge. It's just the number of stars is gradually getting less and less and less. So in fact, there isn't really a well-defined size. But if I say a couple of 100,000 light years, most people will take it at that.
Fair enough. Okay, so my understanding is that you look at the universe using radiation other than visible light. So how effective are these optical telescopes that we sort of think of as old-fashioned now? In modern times, how effective are they?
Oh, optical telescopes are still incredibly effective. It's just that optical looks at different parts of the spectrum and therefore see different aspects of nature than other parts of the telescope. But optical telescopes can see right back to the formation time of the first galaxies, 10 to 12 billion years in the past. So optical telescopes are still at the center of astronomy. It's just that you have to go outside the optical to get a full view of what's going on in our cosmos.
Okay. So we'll go into that a wee bit more deeply then. What is infrared astronomy? This is one of your specialties.
Indeed, infrared is what I did my PhD in. Infrared, in some sense, is like heat astronomy. It's astronomy at a slightly longer wavelength than the optical. It's wavelengths of a few microns as opposed to a few fractions of a micron. And it helps you peer through the clouds of gas and dust in our galaxy. So you can't actually see right across our galaxy in the optical because there's dust in the way. The dust blocks the light, it stops it getting to you. In the infrared, you can see across the galaxy, you can see to the center of our galaxy, and you can see to the heart of clouds of molecular gas where stars are formed. So infrared allows you to see a hidden part of the universe that you can't see in the optical.
Brilliant. Okay. So why are galaxies dusty then?
Well, that's a good question. That's an interesting question. In fact, dust is found all over interstellar space. Dust, in some sense, is the debris that is created by stars when stars die. Some of the particles that are made up there, some of the silicates, for instance, are made there, turn out to be the seeds around which dust can grow. And so in all the clouds of gas in our galaxy, there's actually significant amounts of dust. It's about 1% by mass, about 1% of it there, and that's enough to block out the light. So it turns out that when we look across the universe, we look at galaxies, in fact, dust, small dust grains, about 1/10 of a micron, very, very tiny in size, about 1/10 of a micron across, are actually blocking out much of the optical light coming from those galaxies, certainly in their central regions.
Brilliant. So now, I have to say, I always understood that space was a vacuum, but there are lots and lots of molecules in space. We just maybe fewer. Is that the case?
Well, space is indeed a vacuum. And even in the regions of space where there's gas, it's still a better vacuum than we can make in our laboratories. It's just that space is so incredibly big, so incredibly large, that there's vast amounts of material out there. But indeed, inside space, there are all sorts of gas particles, there's atoms, and there are molecules. And molecules, in fact, are what I've been studying for much of my professional career. Molecules are some of the densest regions of interstellar space. But when I say dense, that might mean, say, 1 million particles in every cubic centimeter. Now, you might think that's a lot, but in fact, in our atmosphere, in the air we breathe, there's 1 million times roughly more particles in every cubic centimeter than interstellar space. But indeed, interstellar space is full of material, and that gas is actually the primordial material from which all the stars are born from.
Brilliant. So what are the most abundant molecules in the galaxy then?
Well, the most abundant one is very simple. It's the hydrogen molecule. Two hydrogen atoms come together, and in fact, that makes up about, I think, 99.99% of the molecules. However, the hydrogen molecule is essentially inert. It's very, very hard to see. So in fact, we study interstellar space, we study the molecules there by looking at other trace molecules. And the most important one of all is actually CO, carbon monoxide, what can be produced in auto exhaust, but in fact, it's actually rather abundant through our galaxy, and it's the prime molecule we use when we're trying to see where the molecular gas, the star-forming clouds are across our galaxy.
Okay, Michael, that's all the questions I've got for you today. Thank you very much for doing this interview. I'm sure we've all learnt loads from it. So I'm going to sign off here, and hopefully we'll see some other people maybe and find out even more about space in this time. So thank you, everyone, and bye.
Thank you, Anna. Goodbye, everyone.